Hello. Yeah. Hi, everyone. Sorry for the delay. I just got delayed due to my system issue. So, good afternoon. Good evening, everyone. Am I audible to you all, by the way?
Yes, sir.
Great. So, just give me a second. I'll share my screen and we'll start with the session right away. Is my screen visible to all?
Yes, sir.
So yeah, today's topic is Venturi analysis in using CFD, computational fluid dynamics. So in today's session, we are going to see the overview, Bernoulli's principle, then CFD overview. We're going to see then how to set up the simulation, like what are the pre-requirements that we need in order to set the simulation up. And then using a skim scale, that's an open source kind of online virtual platform which everybody can use for conducting CFD analysis. They don't need to you don't need to have a high-end system also. Just that sufficient amount of RAM would be that can hold the Google Chrome. That would be sufficient, and like you don't need heavy softwares basically. So SimScale is something they have their own servers. And they basically lend their computational power via a web service. So there we actually talk about, and then talking about actual discharge calculation, how we are going to do that. Okay. So starting off with, everybody knows right, Bernoulli's principle. So basically, if you have something. So, can anybody tell me what the Bernoulli's principle states? Yeah, you guys can unmute yourself and tell me. Like, what is the basic concept of Bernoulli's principle?
Hello.
Yeah.
Sir, am I audible?
Yes, you are.
Sir, the Bernoulli's principle statement. Hello.
Yeah. Tell me. Hello, I'm audible to you. Anyways, talking about Bernoulli's principle, let's just.
Hello, sir.
Yeah.
Hello.
Yeah. Tell me. Hello, I'm audible to you.
So Bernoulli's principle states that when the area decreases, the velocity will increase, and also pressure decreases. And on another side, when the area is more, the velocity will become velocity reduces.
Yeah, exactly. So basically, it's a trade-off between pressure energy and velocity energy. So the concept works on a simple idea. So if you have a channel, something like this, your fluid is moving from this point to this point. As the area gets narrower, the fluid's velocity increases and its pressure basically reduces. So, and at every section that you make, the discharge is constant. So whatever fluid that is going to move forward, basically your discharge is equal to area to velocity, right? So as your area, so basically when your area reduces, your velocity will increase and discharge will remain constant. Same thing, if your area increases, your velocity will reduce and your discharge will be constant. So this is something we are going to just see how it is going to happen on a virtual platform. Okay. So before that, I just wanted to give you all a pretext of or context of what computational fluid dynamics is. So computational fluid dynamics basically is a branch of fluid mechanics which deals with numerical analysis. So how it does things is when you have a physical problem, something like this Venturi meter, right? You need to actually analyze the velocity. Basically, if you are operating at, let's say, 10 meters per second velocity, your fluid is moving at 10 meters per second velocity. and you need to test the different parameters or different properties of that fluid when it goes from A point to B point and basically flows through the Venturi, right? So this kind of phenomena or this kind of properties you can actually understand or learn, actually visualize using computational fluid dynamics. So it can be any real-time condition. You can take a vehicle moving on a road, and you can perform an external aerodynamics analysis where air is moving on the top of the surface of the vehicle. So that is a real-time scenario. So if your vehicle is moving at, let's say, 24 kilometers per hour, then at that speed itself, basically the air that is going to bombard over this surface of the car, that you can actually analyze, and at what force it is getting impacted, what is its velocity, what's its temperature, what's its pressure. So all these things you can actually analyze, and that too at different sections over the particular body. That is a basic and very generalized way of explanation, or very like application oriented way of explanation of what CFD is. So using like how are we going to predict or how are we going to calculate these kind of numerical values like parameters, right? So we like computational fluid dynamics uses numerical methods to actually resolve the quadratic equations into linear equations or linear matrix formulations, and then that linear matrix formulation is basically used to solve the it basically calculates the value of the parameter for pressure, let's say, at a particular point at a particular section. So that's how it is basically being used. CFD is made possible because of high-end computational power and high-end computational resources. Like you have supercomputers now, so basically they can calculate at very fast speed, and they can also calculate very complex equations. They can solve very complex equations. And as most of you might know, numerical methods are iterative methods. Basically, you have an initial guess value, which you substitute in a preset formula, preset equation, and based on that, you will again update your initial value, and that's how it gets updated, and that's how you are predicting the difference between the previous value and the next value that's going to come. And as the difference reduces, the solution becomes converging. The solution becomes accurate. So this is how numerical methods work. Now, in order to compute these, in order to actually calculate on those lines, you need to perform hundreds, thousands of calculations if you were to do it manually. And that too, finding the parameter, one single parameter at a particular point, not even for a particular, for a whole body. Just for a particular point, you need to calculate it at least 100,000 times, and then you will be able to get an accurate answer. Now, you will need a supercomputer, you will need advanced computational capability in order to solve it, to reduce the time that it's going to take, and also improve accuracy. Now, there are stages in CFD. So first stage is pre-processing. Pre-processing involves two most important aspects, like geometry preparation, repair and creation, and meshing. So basically, geometry making, you need to actually create an environment. So you need to have a flow field in order to actually simulate the fluid flow. What CFD works with is basically something called as negative volume. Negative volume is referred to the fluid space that is going to be evaluated. So there is this, if you have a, let's say, if you have a pipe, okay, and you need to perform a simulation using this pipe. So the material of the pipe or the circumference of the pipe is not necessary in this particular case. What is necessary is this inside space. What you do is you neglect the actual body of the pipe, but you'll take in the inside of the pipe. So basically, whatever fluid volume it is occupying, that particular volume you will consider, rather than considering the actual solid geometry of the pipe. So the inner space inside of the pipe is considered as a negative volume in that particular case. Now this is referring to the internal dynamics, like. But what about external things? So something like this, like if you have a ship, so what you will do is you create a volume around a ship or around that object. Like I have given the example of a vehicle moving on the road. So you'll create a volume around that object in order to analyze the external behavior of the air that is moving over that, or basically how much amount of drag resistance it is providing to the vehicle. So that that particular thing you need to create a negative volume basically. So that particular part only we are going to analyze. We don't analyze what is goes on inside the ship. Maybe we do analyze that, but at an advanced level where you take into account different openings in the ship, different pathways or vents through which the air air enters the insides of the ship. In that case, you might consider insides of the ship, but that is again a complex phenomena. For simplicity, we'll just assume that we don't go inside the ship. We just for external aerodynamics, we'll just have it. We just create a negative volume around the ship and analyze it accordingly. That is all about the geometry making. So when you have a CAD file, you use that CAD file to actually create something like this. When even for internal flows, you will also establish something like this. So your fluid is moving inside this inside this cavity, and it is moving over this turbine blades. So this is also you need to actually consider while making the geometry, preparing the geometry. You will get to know about it when we are actually moving on to the simulation part. Coming to the meshing. So meshing is basically once you have a negative geometry. Now this is a negative geometry. If you can see the volume that is shaded in gray is the volume that you are going to analyze, and this is the empty space. So this particular point, over here there is no material added, so this you won't be analyzing. One more thing, the material that you are giving over here is fluid, it's not a solid. So whatever gray shades you are seeing here is a fluid, it's not solid. And in meshing, basically what happens is we actually divide this geometry into small parts, as you can see over here. This we do because we need to calculate the property within that particular within a small particular cell. Because if you calculate the property over this particular big space, what happens is usually your properties have weird graphs, weird curves. Now, in order to assume these lines to be straight, you need to go to infinitesimal small points. So you'll basically take a very delta x dx kind of a small portion of this curve, which you can probably assume as being straight, and then you calculate that area under that curve. And this goes for each and every property like pressure, velocity, everything. So that's why in order to simplify this, basically you divide that into small sections, and the smaller the sections, the better accuracy you are getting. So this is how you basically divide each and every part, and for each and every cell that you are seeing over here, you will calculate different parameters like velocity, pressure, temperature, kinematic viscosity. All these parameters you will evaluate, will calculate turbulent energy dissipation. All these parameters will calculate at different stages. Again, in order to optimize or understand this phenomena, what we as a computer dynamics engineer do is to optimize the shapes. So whenever we have, so basically we divide it in regions. Over here in this particular problem, what I need to do is I need to check the near surface behavior of the air that is going to move past the vehicle. So what I will do is I'll make the mesh denser over here, basically reducing the size over this section and keeping the size bigger over this section. This I do to reduce my computational time again, so that I can get results faster. Because frankly speaking, whatever happens over here, over this region, I don't have that much amount of, like, I don't need that much amount of accurate results for this particular section, but I do need a significant amount of accuracy over this region. So that's why my mesh is dense over here. That's why the cells are smaller, where I can calculate better. So this is what meshing is all about. So yeah, this is what meshing is all about, and this is the general idea about pre-processing. Now, anybody has any questions, they can ask me. So I think there is a question in the chat, sir. Just like negative volume, is there positive volume present? And so please define positive volume. So okay, so basically, if I tell you about this, let's say, just a minute. Let's say this is your pipe, okay? If you see it from this angle, you'll see it like this, right? Now, this is your solid body. This is your fluid body, right? So there is, first of all, no such thing as positive volume, because we don't define positive volume, because we don't need it. We don't need to define positive volume. The reason being, when you are dealing with fluid flows, you are applying equations to fluids. So when you have a solid geometry, or when you have a solid part that is present, those equations will not be able to, those equations won't be applicable to the solid body, solid geometry. So it itself becomes redundant in that particular scenario. So you are just wasting your time and resources by including the solid geometry, and due to which what happens is, in CFD we ignore the solid geometry and we only consider the fluid geometry, the fluid section, and that's the biggest impactful thing in CFD, because that reduces a lot of computation time. Yes, in some cases, in some advanced cases, you would need solid bodies as well, because sometimes what happens is solid bodies do interact with fluid, and there are moving parts involved. So let's, for example, turbine. Turbine moves, and due to the water impacts on the turbine, and due to which it moves. So in that case, you actually need to define the boundary, but still you are just defining the surface of it. You are not considering the solid of it. In that case, what happens is, so I'll be better able to explain this. Yeah, over here, as you can see over here, the turbine is there, but it is hollow inside. So only the surface of the turbine is considered over here, just because of the contact surface. So it is also called as a contact surface. Basically, the surfaces that are in contact with the fluid, those surfaces only be considered. Inside it's hollow, inside it's empty. Don't consider that. Because again, we don't need that information. We only need the connection, contact information. That's what. So that is about the positive and negative volume. Does anybody have any other questions about this? Okay. So when you generate a mesh, then what is next, right? When you generate a mesh, you will move on to the solving part of it. So solving consists of setting up physics and solution calculation. So till this point, what we have done is, we have first of all defined the problem and created a geometry. Using that geometry, we defined which section is fluid, which section is solid, and disregarded the solid section, only considered the fluid section. Then taking that fluid section into account, we divided into small parts so that we can calculate the properties of that, right? Here, the actual calculation is going to happen. So what you need to have is something called as boundary conditions. So in your theoretical problems, you might have seen that you establish boundary conditions like adiabatic condition you have where there is no heat transfer, or boundary condition something like you have X amount of velocity at a particular from particular point. So for if a fluid body is moving from A point to B point, you will have X amount of velocity over here and Y amount of velocity over here. So something like that, you have values. So that those are called as boundary conditions. Now in here also we need to set up boundary conditions. So if you take an example of this car itself, you will need to basically this surface is your inlet. This surface is your inlet. This surface is your outlet, because the air is again going to move from something like this, right? So over here at this is your inlet boundary, which you are giving any of the variable. You are assigning any of the variable like velocity, like pressure. You're assigning that over here. Again, for outlet, you're again assign that, and this basically becomes your wall. The edge. This edge becomes your wall. This again bottom edge becomes your wall. Again, the surface of the car, this edge becomes your wall. Because on the wall there is nothing happening. We don't assign anything to the walls. Walls is basically there is no fluid moving past that point, past that line or past that surface. So that's why they are called as walls. So these are basic boundary conditions that we need to understand before going on to further things. Once you define these boundary conditions, like X amount of velocity I have at my inlet, and it is going to propagate in this certain manner. So you will select appropriate values for those boundary conditions. So in order to mimic real life conditions. So let's suppose if your vehicle is moving at 24 kilometers per hour, again the air that is going to be impacted on the vehicle will be impacting at the same speed, right? So what we do is, so if your vehicle is, we don't give the speed to the vehicle, but we give the speed to the air that is going to be impacting upon the vehicle. So this is the analogy that many of the most of the CFD concepts use. So that your object is stationary and your air is going to be moving over the object instead of keeping the object moving. Because if you're keeping the object moving, in that case it becomes time dependent. But over here you can actually run a steady state analysis as well if you give the velocity to the air. So there basically you can then add conditions like turbulence, you can add gravity, you can even add different conditions like what is the temperature of or if there is a heat source, if there is a multi-phase flow, like if your water is converting into vapor at certain point throughout the flow, so that comes under multi-phase flow. If your water is getting absorbed into porous media, so that is again the different kind of simulation. So there are different variables, different conditions which we will define, and we will giving those conditions as inputs to the system, and then based on those inputs, the overall system will solve the rest of the output. Because any which ways, unless and until you have variables defined, because this is simple. If you have three unknowns, you need to have three equations in order to solve those three unknowns. So it works the same way. If you have one single equation, if you know two parameters, you will be able to easily calculate the value of third parameter. Let's say A plus B is equal to C. If you know A, if you know B, you can easily calculate C. Or if you know A, if you know C, you can easily calculate B. So it is something kind of that. So you need to give some kind of values, inputs, in order to solve, in order for the simulation or the overall equations to be able to solve themselves. So by the computer's power. Again, you need to establish real life conditions like what domain it is. material, like if it's air or if it's water, you need to establish that. If there is a symmetry, like if your object is symmetric, then you can probably calculate the values on the first half, and you can essentially replicate those values on the second half using CFD, using a symmetry condition. So in that case, you are again spending half of your energy to get full values, a complete simulation results. So that is another. So that comes under setting up physics. Once you have set up the physics, once you have established that this is my simulation virtual environment, basically this is how my vehicle is going to move. This is its this is the velocity of the air. These are the properties I'm applying. There is something, a temperature involved. So all these things, once you define, you'll go to solving part. In solution calculation, there are something called as governing equations. They're also called as Navier-Stokes equations, which are universally applicable to all fluid flows. Now, based on those Navier-Stokes equations, there are different models developed using some assumptions. So Bernoulli's principle is also an assumption. It's essentially a simplification of continuity equation. Even your continuity equation is not simplified. Like conservation of mass, conservation of momentum, conservation of energy. So all these three equations are a basic physics, right? So those equations are called as governing equations, and one single equation or like a set of equations developed by Navier-Stokes combine these equations together to give you a balanced equation that solves for the different properties. Now, those governing equations, they are then applied to your model, to your real-time condition. Then you will set up a convergence criteria. Basically, you are setting up a finite calculation. So if you want to calculate for let's suppose 1,000 times, a particular parameter you are calculating 1,000 times, and you are establishing the criteria in such a way that the 999 time the value that you are getting for x and the 1,000th time the value that you are getting of x will have very less amount of difference. So let's suppose x 1,000 minus x 999 will give you 0.000001. So this is a very less amount of error, and there your solution becomes acceptable. Then your solution becomes converging. So this is what is called as convergence in CFD, where these iterations that I've speaking about numerical methods, they are solved accordingly elsewhere. And this is how you are setting up convergence criteria. You are giving a tolerable difference. Like you are actually feeding the software that I want the difference between these two successive variables to be 0.0001. And if it's achieved, you can stop the calculation for that particular variable and move on to the next variable. So this way you're controlling the solution parameters. Otherwise, if you don't control it, it will continuously goes on calculating, and infinite calculations you will have. So in order to avoid that, your system will basically crash and it will generate infinite amount of data. So in order to not have such kind of scenarios, there are limiters provided. In post-processing, what you do is basically something like this. So whatever simulation you have done, then using colors, you will be able to understand and analyze different parameters like velocities. This particular graph is for velocity. So the colors draft in such a way that blue means very lowest of the low value of the velocity, and when it goes from blue to red, it becomes higher and higher and higher. So red means higher, blue means lower. And accordingly, you can actually put anywhere in this domain, you can actually put a point and actually calculate the value of that pressure. I'll show you how it is done in the analysis that we are going to do in just a bit. This is how you are going to do the post-processing. Now, before actually moving on to the analysis, anybody has any questions?
No, sir.
Okay. So, today's analysis is a Venturi meter. So basically, we will create a geometry. we'll create something like something on similar lines, something like this, and we will simulate this. So we'll have an inlet velocity as 3 meters per century, and we will see how the pressure changes from point A to point B, and we will actually calculate, like, this is your point B, this is your point A, and we'll actually calculate the discharge using the values we are getting from the actual simulation for the pressure. So we only are defining velocity, we are defining the outlet pressure, that too at default condition it will calculate itself, and then actually you are going to get some X amount of value for pressure P1 and Y amount of value for pressure P2, and using that you'll use the discharge formula to actually calculate this value of Q. So let's just move on to the next portion. Now, for simplicity, I have already completed the simulation, but I will simultaneously give you the complete idea of how to do. Basically, this is a SimScale website. So please explain all the types of model used, like here, omega, SST, etc. Okay, if time permits, I will get back to this, but as of now, the simulation is more important. I'll get back to you. Basically, this is the online platform that I was talking about. You can log into this, you can go to the dashboard, and you can basically you can click on Start Simulating Now. So if you go to Start Simulating Now, you will click on New Project. You will define the project title, which I've already done over here. Whatever the title of the project is, you'll describe its description, and you'll be basically creating the project. Once you create the project, you will come here and you will again click on the basically this is how the UI will look like. So over here, your tool tree will be there. On the left side, on the right side, you will have this topological, like from geometry point of view, whatever things that are needed to be observed, those will be here. These are some views that you can change, like front view, side view. You can select the face, you can actually change it to wireframe, and all these things. From here, you will able to understand the direction and the orientation of the geometry from the right bottom corner. Now, I'll click on Add Geometry, the plus sign over here, and I'll import the geometry from my PC. So the one advantage SimScale has is you can directly import a CAD file or any CATIA or any SolidWorks file. You can directly import. Otherwise, in softwares like Ansys, Star CCM, you need to convert that file into .stp.igis in order to actually be able to make it supported for the particular analysis. So while you're importing the geometry, it takes some significant amount of time. Once your geometry is imported, you can go to Edit in CAD mode and edit your geometry. So why this is important is because you need to actually understand if there are any gaps between your geometry, if there are any irregularities, because when you are actually importing a geometry from one software to other, they are bound to have some variations. So there might be some fixes, some oversimplification of edges, of points, joints. So there you might need to do some repairing. So you'll do this, you'll just click on gaps, detect gaps, and once you get a green signal, there are no gaps. Again, you'll check for interfaces, and there it'll tell you that there are no interfaces. So basically, this is how you can test your geometry. Now you exit from this UI. And here you'll come to this particular one. Now you can go to simulation and add simulation. So here you'll have multiple options like multi-phase, compressible, conjugate heat transfer, subsonic. So in here you'll select incompressible, the basic simple one, and click on create simulation. Okay. Over here, when you do that, this tree, it gets expanded, and over here also you will see the title of your simulation. So you can make it, you can keep it incompressible, or you can edit that title as well. Over here, when you select incompressible flow, you will have to select turbulence model. Now, turbulence models are basically using different assumptions. The Navier-Stokes equation, the main equation, is dialed down basically, and using some simplifications in that equation, it is basically reduced to a 2 equation point, or 3 equation point, or 5 equation, 4 equation. So that way you basically, and it is categorized in this manner only: K epsilon, K omega SST. So that's sort of things we do. So yeah, for this we will use K omega SST. We will use steady state, and basically time dependency we are not keeping. We are keeping it as a steady state itself, because for the sake of simplicity, we just click on OK. Moving on to the geometry, you need to make sure that your geometry is having this green tick. If it is not there, then there is some issue with the geometry, or it is properly not loaded or something. So you need to check that. You need to make sure that there are green ticks. Where there are green ticks, those conditions are okay. That doesn't mean you can't modify them, but still they are okay. First, you'll go to geometry, you'll check, yeah, it is okay. Then you'll go to materials, you'll add material as water. And simply, you'll just select it from the list over here. You can actually click on that, click on apply, and here the water will be added. When you have this, you can actually change the density of the fluid. You can actually change viscosity model as well, in order to make some changes, but still we are not going to do that over here. Coming to the initial conditions, so here are these initial conditions which they have already added. So there are 3 velocities, as you can see: ux, uy, uz. Then there are, to get this, okay. Then there is gauge pressure, there is turbulent kinetic energy, and specific dissipation. So all these 4 properties are already added by default. Then you will go to boundary conditions. If you click on boundary conditions, you'll add the boundary condition as velocity inlet. So you click on velocity inlet. Here another pop-up comes up. You will give it will be there like boundary conditions is velocity inlet, velocity type is fixed value. Fixed value meaning you are assigning a particular value to that. Okay. Now, from this orientation, our fluid is going to move from bottom to up. If I turn it horizontally, you will be able to see that we are moving in a positive y direction. Okay, from top right bottom corner you are seeing we are moving from left to right. So it is from this orientation in this context, you are moving in y direction. So you will give uy as 3 meters per second. Again, you need to assign a phase as an inlet. So this is my inlet phase. So I will select this phase, and we keep over here. So now you can see that this phase is assigned a 3 meters per second velocity. Again, I'll go to add conditions. I'll again same thing I will do. I'll add a pressure outlet condition. You have to do a deeper understanding or deeper research on these, like why it is velocity and pressure, why it is not pressure and pressure. All these things are there. So there are different set of values we can assign to. But yeah, for simplicity, I'm just keeping it this way only. So over here, you are not going to give any value to the pressure outlet because you have given a certain amount of velocity over here. That is your first inlet condition, inlet value. Based on that initial guess of the parameter, rest of the values will be automatically calculated. So your initial guess for the pressure will be default, which is atmospheric pressure. So you don't need to give any gauge pressure value. But you again need to assign the phase. So this is my outlet phase. I assign that phase over here, and this is my velocity inlet, pressure outlet. Now, rest of the phases that I have are still unassigned. The most important thing you need to understand in CFD is all of your phases should be assigned a certain something. So certain boundary might be complications or there might be simulation errors in other assigned the values. So I have given my inlet, I have given my outlet. Rest of the faces are my walls because through them there is no flow of the fluid. So I'll select wall and automatically no slip condition is applied. Wall function or turbulence wall function is applied. So basically we are going to assign these faces. And click on OK. So you have assigned your velocity inlet condition, you have assigned your pressure outlet condition, and you have assigned your wall. So this is how you are going to set up. So one more thing, this geometry that you are seeing, the surfaces that are highlighted by me are the boundary surfaces. So you can assume that as a solid, but it is not technically solid. It is imaginary boundary which we are established for this, basically which is containing the fluid that is going to move throughout this. And this solid object that you are seeing is a actual fluid body, a body of fluid. Then coming to again simulation controls, you don't need to worry about numerics. Coming to simulation control, we'll keep it default itself. So here you are setting up the iterations. So 1000 is basically 1000 number of iterations. Your delta t is 1 second. So every 1 second you are going to calculate the rest of the things. Like at every single second you are going to calculate pressure, velocity, and the kinetic energy, all these parameters. There are no additional parameters we have added for now. For in this particular simulation, we are only calculating pressure and velocity. Then this is interval. So if you want to record certain values between intervals, like let's say at every 50th interval, you need to save the value, save the data for whole calculation, and that you can do. So what happens over here is for each and every second, the parameters will be calculated throughout the body, and I'll talk about that more about that later. So for now I'll just close it. The first thing we need to do here is create mesh now. So once you click on mesh, you can actually select the algorithm to be standard or hex dominant. Usually hex dominant is better because it captures the values better. Then you go to mode, you go to like sizing, you go to manual mesh sizing. You can actually manually establish these sizes. So as you can see over here, the coarser, the finer your size is, the smaller. This is basically you're establishing the smallest cell size. So the model that I have used is of let's say 100 mm by 60 mm. Horizontally it is 100 mm, vertically it is 60 mm. So based on consideration, keeping that into consideration, I'll keep my minimum edge length as 1 mm. So the cell that is going to be created will be 1 mm. And I'll just keep everything else default. I'll click on generate and it will generate. So because we don't have a lot of time, I have already generated a secondary file. So this is how the mesh would look like using that parameter. So I've used hex dominant, I have used manual mesh sizing, I have used minimum edge length as 2 mm over here, and maximum edge length would be 1000. So maximum edge length won't matter. Minimum edge, as long as you have defined minimum edge length, accordingly the overall mesh will be optimized, and this is how it is going to look like. This is how a hex dominant mesh looks like. Okay. So I haven't also added any additional refinements. Basically, you can add layers to it. You can do a lot of things. But for now, I have, because this is a very simple simulation, I have not added any additional parameters. Now, once you go to simulation runs, basically whatever parameters or simulation control you have established over here, based on that, you will go to simulation run. So once you start calculating for 1000 iterations, the whole calculation will be there. So it's nothing much. basically you have already set up everything in simulation control. Then you just need to go to simulation run and click start a new run. So as you can see, resource estimation based on the mesh parameters, it can estimate about 28 to 48 minutes. So this being a very simple calculation, it gives you solutions in the matter of minutes. But if you talk about, again, if you increase the number of cells that I was talking about, that is basically if you reduce the size of the cell, then there becomes a lot more cells you need to calculate on, and there the duration increases. So when actual researchers or actual things are being pursued, some simulations might take days, like 2 days, 3 days non-stop. The simulation is going on, the calculations are going on, and then after that you will get the result. So it becomes very computationally very heavy. So accordingly, you need to actually have a better system. So if you have like a 32 core processor, then that processor might be able to calculate that level of advanced computation within matter of hours. But if you have like a 16 core or 4 core, 8 core setup, then that setup would essentially take longer time, in the matter of days, in the matter of weeks also it might take. So this is the context of these things. So basically, you just need to click on start and it will start running. So it will usually, for this particular calculation, it took me around half an hour. And basically, if I expand my simulation run over here, as you can see, I've run 2 different simulations. So let's just basically, once you complete the run, you will have this window popping up, run to finish, and you can go to then post-processing for the results. When you go to the post-processing, here actual analysis happens. Okay, so let me just do one thing. So as you can see over here, this is a pressure reading. As you can see over here, pressure reading. This is my inlet. So at inlet, whatever based on the velocity that I have given, the simulation calculated the pressure, and it came out to be 5.1 into 10⁴ pascals. Then slowly it moved towards the throat of the Venturi, and due to the Bernoulli's effect, here velocity increased and pressure reduced. So as you can see, red is higher and blue is lower. So your pressure basically reduced while moving from here to here. And this particular things you can actually see. This is how you reduce a particular thing. Now, if I change it from pressure to velocity, you'll be able to see the velocity y. You'll be able to see the actual velocity propagation in y direction, in y axis. So you can see you have established initial velocity of, let's say, 3 meters per second. As you can see over here, it is mentioned 3 meters per second in the range. Slowly it increased to up to 13.42 meters per second. So your maximum velocity at this particular point is 13.42 meters per second. So this particular calculations you will be able to get. Okay. Now, what do we need to exactly extract from this? So if you go to the actual calculation, this is the formula for discharge calculation. Here you will need pressure 1 and pressure 2. Okay, in normal circumstances, theoretically you will be given either pressure, either velocities, so that you can calculate the rest of the things. But so basically something like this, if you have velocity, you can actually calculate that pressure difference using this formula, half rho v1 square into this particular thing. So over here, what we are going to do is we are going to take this pressure difference and from these numerically calculated values and feed that data over here. So we know the area 2, we know the area 1, we know the density, and that is required over here. but just we don't know the pressures. So based on this simulation, we can just take the pressures. So how to take those pressures? First thing is switching back to the pressure gradient. Over here, as you can see, you can actually click, you can actually make use of this inspect point function and click it where you want the pressure to be calculated. The pressure at over here is around 48,755 pascals. Then you note that down as your pressure 1, P1. Then same thing you do for this particular section. Now, how do I calculate this? If I can just do it, I can just do it like this also. Or if I want to calculate based on this side, then what I will do is I'll go to cutting plane. I won't cut it in X. I'll cut it with Y, and then I'll take again click on inspect point and put it over here. If I click outside, inspect point. So here I'm getting a negative pressure of minus 25,000 pascals. So I'll just take the difference of those pressures and I'll feed that pressure into this formula to calculate my discharge. Now, how to validate that whether it is correct or not, right? Basically, you can validate that using this particular formula. So here you know the velocity 1, that is 3 meters per second. You know the rho density that you have used 997 kgs per this thing. Then you have your area 1, area 2. You know the throat area. You know the initial area. You know because you know the dimension of the Venturi. Feeding that all data, you will calculate this delta P. Then you will calculate the delta P from your numerical values and compare both of them. So let's suppose your theoretical value is coming up in the range of 75,000, theoretically calculated, and your virtually calculated comes, let's suppose 60,000 pascals. So there is a huge difference between these two values, 60,000 pascal and 75,000 pascal. So maybe you need to actually improve on to the simulation. So how you are going to do that? By defining your mesh properly, applying different set of boundary conditions, as in different set of solvers, basically, like K epsilon, K omega models. You can use different models you can use to test your theories and basically try to reduce this difference. And that accordingly, once the difference is very minimal, let's say you are getting 75,000 and with the theoretical and 71,000 with the actual numerical value, then that is acceptable. Because with this, we are only getting approximate values. So we are only limited to that part where we won't ever get exact values, because for that, you need to have extreme calculations and you need to have exact calculations. So we are only working on approximations. So the closer the answer is from your numerical simulation to the actual real one, the better results you have. Basically, the better is your accuracy of the model. So this is how you are actually going to predict and validate that if your model is correct or not. The advantage with this is you are able to actually see at any given point the pressure without having to physically calculate it. Pressure may be velocity. So all these properties you can specific dissipation rate, turbulent kinetic energy, kinetic viscosity. So all these things you can check. That is the biggest advantage of CFD. So that's all about the tutorial. Now, anybody has any questions, they can ask. Which solver does this simulation use? Jacobi, GS method, or CN method? And what is the scheme? FTCS, BTCS, or CTCS? Actually, I'm not sure about that. Sir, in the end, please provide the recording link of this session also if possible. Yeah. So this session will be available on YouTube as well as you can just YouTube it on Elite Techno Groups. So so you'll be able to do it. So yeah, that is there. If anybody has any questions about this simulation, they can ask me. In the meantime, I'll be sharing the feedback form link. Aman asks, sir, please explain all types of model used like K omega assist, etc. Okay. So the basic idea with K epsilon and K omega assist is your K epsilon model is capturing the values correctly throughout the fluid model. Your K omega model capturing values near wall boundary condition, it captures accurately. In majority of the cases, if there is like sharp edges, if there is sharp geometrical changes, K epsilon model tends to give unrealistic results, due to which you need to use K omega, because there are sharp changes in the geometry and there are narrower paths. So there you need to use K omega. But again, K omega does also have its own limitations where it can't give you realistic values with the open fluid flow cases. So that's where K omega SST model comes in, which is a shear stress transport model, which basically combines the advantages of both the models of K epsilon and K omega, and gives you a better accuracy, better results in terms of near wall behavior of the fluid as well as the internal fluid behavior. So yeah, that is a basic definition, basic difference that at this stage I can share, because if you go into deep about it, it will take a lot of time to explain everything. So yeah, so I'm sending a feedback form link in the chat. Using this link, you guys can avail free counseling from our end, where our experts will get in touch with you, get in contact with you, and give you the necessary skill or the necessary understanding of which area you need to go to, which area you're interested in, and through which you can also claim a free course in that same domain, like CFD, maybe CFD, maybe design, maybe data science. So that way you can actually have it. So yeah, basically I would urge you all to fill this feedback form link and get a free course out of it. If anybody has any more questions about this, they can ask me. I'll be here for a couple of minutes, and then I'll be concluding the session. What about LES models? Okay. If I talk about LES, I need to be going back to a little, where I need to just give better context of concepts, approaches. So there is Euler approach, there is Lagrangian approach. In Eulerian approach, you will have you'll define basically a set of you will basically calculate the overall parameters on a certain set of volume. But if you go with Lagrangian approach, you will have to calculate it with each and every point. So you have to trace each and every fluid particle completely from start to end in order to understand its behavior. So LES kind of is a byproduct of a Lagrangian approach, which is basically you need to trace fluid particles, each and every individual fluid particle, to calculate the properties of the fluid throughout the domain that you're going forward with. Now that takes immense amount of time, immense amount of calculation, but it is the most accurate model that you can build. But it takes years to build. It takes years to actually resolve that. So more generically, Reynolds stress models are preferred as opposed to LES models, because Reynolds stress models are or basically simplified. So yeah. Okay. I hope that answers your question, Naman. And yeah, so if there are no further questions, I guess we can conclude the session. And I thank you all for participating. I thank you all for coming here. And do check this platform out. Actually, it will help you out a lot. It also has public projects you can go through. You can just understand how those things work. Get a head start on like practicing simulations. So this is the easiest and most more accessible format if you want to go for simulations. So yeah, with that, I take your guys' leave. Thank you very much. Keep learning, keep exploring, everybody. Have a nice evening. Bye bye.